All right, I'm just going to read off the question on the slide here. In a Monte Carlo simulation for tolerancing analysis, let's say you generate 1,000 Monte Carlo systems, but produce only one in the factory. What does this mean and what can you do about it? So this question is for those of us who design and develop and produce uh, complex optical instruments or complex any instrument at very low volumes, right? And I hear a lot of people saying, well, if you produce very low volume, then what is a Monte Carlo simulation? Because how do you calculate yield from this? Well, the thing is, Monte Carlo simulation is not just about calculating yield. It's when you've got a very complex instrument with many, many variables, and you want to find out for one instrument what is the worst combination of variables and tolerances, therefore, producing the worst instrument. So the answer that I would give to this question is assume that the produced system is the worst system, right? Even though it's 1 out of 1,000. Okay, here I use 1,000 because it's just a random number I just pulled from the air. It could be any number of Monte Carlo systems. In fact, the more complex your instrument is, the more variables it has, and therefore the more number of Monte Carlo systems you should be simulating. It could be tens of thousands, it could be 100,000, right? So that's what I would do. And if the worst system meets the specification for the instrument, then you're done. If you want to, however, reduce cost, you might want to look more into how you can improve certain things. But if your worst system it does not meet the specification, then you would try to fix it with reduced tolerances, which has a caveat. I'm going to get back to that in a second, or fix it with compensators, which is the usual thing. Okay. All right. First, reduce tolerances. The caveat here is that when you perform Monte Carlo simulation, uh, the big assumption there is that every part is produced in a very stochastic fashion. It's completely random under some kind of distribution. And so every single part that you assemble and how you assemble it is also completely random in the distribution, which means it's quantifiable randomness or quantifiable statistics. It's not like unquantifiable statistics. Like, for example, what's unquantifiable? Well, we don't ever know when an asteroid is going to hit us. That's a completely random event that's unquantifiable. It's unreliable how you quantify it, right? History does not necessarily mean um, it's quantifiable. You have to have repeatable history, like throwing dice or tossing a coin. These are repeatable histories that you can quantify. So we are assuming here that every part that you take from your vendor is a Monte Carlo part. That means it's a randomly produced part under some distribution, and how you make it, how you fit everything together is completely uh, justified by some kind of random stochastic process that is repeatable. Every single day, your technician who comes in and puts a part in the instrument, he or she puts it in the same kind of way. Okay, it might be off this way or off that way in some random fashion, but it's always within this tolerance. But is that a good assumption? Maybe not. Okay, it may depend on the mood of the factory worker. It may depend on the mood of the manager, right? Things could drift and change. The whole distribution could shift and change. So that's the caveat about fixing all these things with reduced tolerances. It may not be fixable. All right. So normally we would identify compensators. What's a compensator? Like focusing is a compensator. You've got an imaging lens, you fit it into an instrument, it has to be focused, right? If it's defocused because of tolerances in the lenses, curvatures and thickness and things like that, and if its effective focal length is perturbed and changed, the focus will change. But you can compensate that by adjusting the focus, right? Other things like mirrors, when you got mirrors inside, you can always get a technician, and they're really good. Technicians are really, really good in what they do because they see the part every day, they deal with the part every day. I, as an R&D guy, uh, learn a lot from technicians because I don't see and feel the part every day. After designing the part, I gotta go do something else. And I come back and I'm asked to fix something. I usually don't really fix it. It's usually the technician who tells me how he or she has fixed it over some time period because of experience. And so I gained that from the technician. What I add in value is maybe the rationale behind some fixes, or maybe justification for why it should not be tweaked this way or that way. That's what I do. Other than that, I don't add any value. in the factory, other than maybe moral support, maybe. Right? Okay, so um, okay, so that's really it. That's all I want to say there. Except for one thing, compensators. The interesting thing about compensators is that if you're doing a tolerancing analysis, and if you're used to the way to the so-called RSS method, root sum square method, where you do a tolerance stack by taking each standard deviation, you square it and you add them all up. That's the summing by quadrature method, right? Root sum square means you add the squares of the standard deviations, so the variances add, and then you take the square root. Okay. What happens when you've got compensators? Obviously, when you have compensators, the final tolerance spec will shrink because you've got compensators, right? So how do you mathematically describe that shrinking of the total tolerance when you get compensators? Well, the answer is that when you have compensators, the compensator actions are negatively correlated with your tolerances. So you've got sigma 1 squared plus sigma 2 squared plus all these squares minus the covariance terms. And that shrinks the tolerance. And I talk about that in these books. All right. This book here, published in 2019, is somewhere inside the chapter. I can't remember which chapter it was. And here, I also talk about that, I think, in somewhere in chapter 3. All right. Uh, or actually, you know what? Maybe you don't have to buy these books. I already told you everything in this YouTube video. So all the basics of what I mean is already described here, so you don't really have to, unless you're a nerd like me. If you want to go into the mathematical basis of what I'm saying, you want to derive the equations, you want to see the logic behind it, the mathematical logic behind all this stuff. It's in these books. So if you're into that stuff, read that, and that's, I guess, all I want to say today. Thank you. Bye bye.